Hi everybody, welcome back. Moving on with nuclear physics today. In the last lesson, or the last recording, I covered nuclear fission. In today's lesson, I want to talk about nuclear fusion. Please don't confuse the two. Fission, like we talked about before, is the splitting apart of radioactive nuclei. Fusion is the joining together of nuclei or fusing them together. In each case, you release energy, which could be useful. Above my head, you can see the basis of this physical reaction. We join in fusion two nuclei of hydrogen. Join them together, you create a new nucleus of helium, and you release an awful lot of energy. You can probably see here that there are two different isotopes of hydrogen. This isotope here, deuterium, has one proton and one neutron. The other isotope has got one proton and two neutrons. In this case, two nucleons, in this case, three nucleons. Two nucleons, deuterium, from the word duo, tritium, three nucleons, tritium, from the word tri. And here, just to make it clearer, I've put the boxes from the periodic table. This is deuterium, this is tritium. Okay. The IGCSE syllabus is fairly vague, as it is with fission. It just says that you need to understand the process. It's difficult to say how much they expect you to understand, so I'll probably cover this in more detail than you need. But I do think it's interesting, and I think that too much information is always better than too little information. Okay. So here we have the process in another form, a bit more clearer, I think. So you can see deuterium nucleus joins to a tritium nucleus. They join together, release a lot of energy, and what's left over is a helium nucleus and one neutron. This process of fusion, when you join two protons together, you get a very tiny loss in mass when they fuse together. And we know from the equation E equals mc squared that the loss of a tiny amount of matter leads to the production of an awful lot of energy from E equals mc squared. So therefore, you're probably asking yourself, if it's so straightforward, if we're only left with helium instead of these dangerous radioactive daughter nuclei that we've seen in fission, why is the world not covered with fusion generators or fusion reactors? And the answer is you need very specific conditions that are difficult to create. And the reason is you need very, very high temperatures and pressures to actually push these two nuclei together, because obviously the positive nuclei, what they want to do is repel each other. So you need to provide the right conditions and the right amount of energy to be able to push them together. Once you create the right conditions to push them together, the strong nuclear force takes over and fusion occurs. The difficulty is creating those conditions. There's two fairly straightforward ways you can create those conditions. You need about 100 million degrees Celsius, and you need very, very high pressures. That's created in the center of a star, like our sun. And the reason it's quite straightforward in the core of a star is because the gravity is so great, it just creates those conditions naturally. The other way you can do it is in the warhead of a nuclear bomb or a hydrogen fusion bomb. I talked a little bit in the last lesson about Little Boy, which was the first bomb dropped in the Second World War at Hiroshima, and that was a fission bomb, as was the bomb that was dropped on Nagasaki. A hydrogen bomb is basically where you, instead of creating fission, you create fusion. This is the mushroom cloud you can see in this picture of the biggest fusion bomb, the biggest hydrogen bomb ever created. It was called the Tsar Bomb. It was dropped as a test in 1961 by the Soviet Union. And basically it was a three-stage bomb. It was a combination of a fission bomb and a fusion bomb. You create the fission conditions. That creates the right temperatures and pressure for fusion to occur. So it's a bit like an onion. It was a three-stage bomb. The first stage was fission, the second stage fusion. When the first stage fusion occurred, neutrons were released, enough neutrons to create another fission chain reaction, which in turn creates more fusion reactions, and so on. That doesn't answer the question of why we don't have fusion reactors. So let me move on to the next stage. Fusion reactions do actually exist, not just in the movies. Obviously in the movies, if you're familiar with the Iron Man movies, Tony Stark was able to create what I think is a fusion reactor in a cave with a box of scraps. Nobody else was able to do that. But what he basically created, this arc reactor, was a fusion reactor. There's two reasons why I don't think it's possible in real life. One is that vibranium doesn't actually occur in the periodic table. And the other is the question of how you create these conditions of high pressure and 100 million degrees Celsius. Somehow he managed it, or at least he managed it in Iron Man 1 and 3. I don't think the arc reactor really occurs in Iron Man 2. But it's such a terrible film, it's not worth talking about anyway. Fusion reactions do actually occur. This is it's called a Eurofusion reactor. It's based in Oxford, in England. It was a European project where fusion actually was created inside a reactor. They managed to create huge temperatures at which hydrogen actually goes from a gas into a plasma. And these kind of donut-shaped rings are huge electromagnets that create the right conditions to push the nuclei together. The problem at the moment is it costs so much, and you have to put so much energy in to create these conditions. You end up putting more energy into the reactor than you end up getting out of the reactor. At the moment, there's no reason really to create these reactors because the oil lobby is so strong and so ubiquitous. We don't really have any scientific push to create fusion reactors. I think the time will come when we need to. Let me finish with a story. When I was about your age, in 1989, I believe, two researchers called Fleischmann and Pons released a statement where they said they'd managed to achieve cold fusion. In other words, they'd managed to achieve hydrogen fusion at room temperature. It was potentially one of the great scientific achievements, but when it was investigated, it turned out that they were wrong and they hadn't managed to achieve cold fusion at all. It's one of the great achievements that could be achieved in physics during your lifetime, and it would change the world if that was actually achieved. Okay, so I think I've covered everything you need to know about fusion fairly quickly in this case. As I said before, please don't confuse it with fission. Make sure you understand the difference between them. Hope that was helpful. Take care of yourselves and your family, and I'll speak to you soon.